title is slightly misleading. So I was in the original version. This title was like against rigorous models of reduction, but I think I don't want to be quite so negative. I think that my ultimate conclusion or my punchline is something like there's complementary approaches to thinking about reduction, or thinking about more generally about anti-theoretic relations, thinking about how we connect theories or different kind of mathematized physical models of the world to one another, described in different domains. But my general theme is something like, and this is something I've been thinking about for a while, but turns out that, I mean, the invitation from James, which thank you, caused me to crystallize some of my thoughts about this. It's that when one has a set of mathematical or formal or kind of general rigorous tools to appeal to, that can sometimes obscure the need to do further philosophical or conceptual work. And my worry is that there are portions of the philosophy of physics community who rely on rigorous methods and don't do that extra bit of kind of philosophical and conceptual work. And my suggestion is that this is particularly pressing in the context of inter-theoretic relations. And the general idea of why that should be particularly pressing in that area is, my sort of thoughts on this are inspired by some themes from the work of Mark Wilson, whose work I strongly recommend, although it's hard to read. Wilson has this idea of physics avoidance. So the idea that when one is engaged in the project of physics in general, there's a limited set of mathematical tools or models or methodologies that one can kind of pick off the shelf, and that what one often in general does is shoehorn the bit of mathematics we have available into a particular physical context, and then does a lot of interesting and inventive work. And sometimes people develop new bits of maths, and what people generally do is, say a given content, you've got quantum mechanics, you've got classical mechanics, a huge amount of work has gone for many, many years into developing the right mathematical tools to describe the world at the kind of quantum level in the appropriate domain for quantum mechanics. And a lot of work has been gone into describing it in the relevant domain for classical mechanics. And what the general practice of physicists is to kind of black box the the overlap between those domains. So to connect up the areas the domains with some ideas without wanting to describe in detail the interaction or the overlap between the different areas where the classical mechanics and the quantum mechanics are appropriately applied. And Mark Wilson calls that physics avoidance. People avoid the really tricky physics at the interface between these domains. And I think that it's precisely in those areas, describing those inter-theoretic relations, where it can be really helpful to be a bit less rigorous, because the more rigorous methods will try and import precise descriptions of what's going on in a context where physics hasn't quite developed those precise descriptions. So that's the kind of general thought, that it can be super hard to be rigorous in these contexts, and so maybe extra rigor isn't what's called for. So that's a general idea. And what I want to discuss is, suggesting in some context application of rigorous methods can obscure the requirement for further philosophical work, thinking about inter-theoretic relations. I think in the context of inter-theoretic relations, rigor can be especially elusive, i.e. illusory, i.e. it looks like we've got rigor, but in fact we've obscured the need for being precise in a different kind of way, not using the really precise tools of mathematics, but maybe using kind of philosophical rigor as opposed to mathematical rigor. And so true rigor being like veridical representation of what the world is like, can be elusive in the way of, it's hard to find, it's hard to catch. So elusive, illusory, that's a fun sort of pun, I'm not sure if it's a pun, anyway. Cool, good. Okay, and so yeah, the explanation for this, I think, physics avoidance Wilson's model, precisely where we change scales and mathematical techniques developed rigorously in different areas to describe the different regimes meld imperfectly and imprecisely. And so where people attempt to be super rigorous in one or other sense about these regimes, they are sometimes misled. That's the preamble. Okay, so I'm going to try and go really quickly and kind of overview-ish about the first bit, because this is stuff I've sort of talked about before and I think is less exciting. And then the second bit is looking at some kind of recent formal rigorous work in the quantum classical reduction regime and saying some very, very non-rigorous things about it, with the goal of trying to elucidate exactly what's going on in some of that work, by Ben Feinstock in particular. Bless you. Good. Okay. So one thought I've had that I don't really express in this is that I'm using rigor in a bunch of different ways. And I think that there is a logical form of rigor, beloved of metaphysicians, and there's a mathematical form of rigor, beloved of mathematical physicists. And I think they're both sets of philosophers who are unhappy with just using words to describe things and just using the kind of non-rigorous shoddy techniques of physicists, and they want to get more precise in some sense. And I think both are problematic or unhelpful in different ways. I have much more issue with the use of logic in philosophy, or in this bit of philosophy and physics, than I do with the use of the really advanced and sophisticated mathematical methods used by mathematical physicists or certain philosophers of physics. And the reason I have that, I'm much more worried about the use of logic is for reasons developed by David Wallace in his Math vs. Structural Realism project, in which he kind of says, maths is the correct language in which to describe the world, or it's a good language to describe the world, first order logic isn't. And so the attempts of metaphysicians to try and describe the world using first order logic are just doomed to fail. Whereas it's not so clear that the same problems beset the mathematical physicists' approach to trying to be rigorous in theoretic relations. But I'm still not sure that works, or I think more needs to be said about that. Okay, quickly on this kind of more metaphysical way of thinking about theoretic relations, we've got Nageli reduction as the kind of go-to way of thinking about how to understand the relationship between different theories. So Dizarji, Bomani, Frigg and Hartman has a very well cited paper in which they say, who's afraid of Nageli reduction? And they try and defend it. And they say things like this. The first kind of bridge law, we've got, Nageli reduction basically has a model at one level and a model at another level, and you try and connect up the entities using these things called bridge laws. How are they meant to work? The first kind of bridge law associates basic entities of the phenomenological high-level theory with a foundational lower-level theory with each other. They identify, for instance, light and electromagnetic radiation, electric currents and and the flow of electrons, gases and swarms of atoms. We refer to this kind of bridge laws as entity association laws. Second kind of bridge laws, that's the scene, their property association laws, etc. Okay. Entity association laws indeed express identities. Gases are swarms of molecules, genes are strings of amino acids, etc. We've agreed that this idea, generalised Nagelian Schaffner reduction, is alive and well. Scientists involved in reductionist research programs do the right thing if they take this as a regulative idea. So the claim of this paper is that the right way to understand theoretic relations, or the right ideal, the best possible way to understanding of theoretic relations, is to construct identities between the entities at different levels. And I see no reason whatsoever why that should work, and I think there is a generally very good reason to think that should fail, and I think that this is a very poor regulative ideal, and I want to suggest, and this is a very vague suggestion, or relatively unfounded suggestion, but that part of the reason they think this is a regulative ideal is that this has the kind of rigour or the kind of air of precision that allows them to feel like, here's something we've really understood. And this is a way in which I think rigour is misleading and unhelpful as a regulative ideal. Why do I think this is so bad? Well, a gas is meant to be identified with what? They say the gas is identical to a swarm of particles, but what is a swarm of particles? Is that just another way of talking about a gas? If so, then we haven't identified anything. Interestingly, you've got robustness with respect to atomic perturbation, so it's not some particular swarm. The same swarm might constitute a liquid or a solid at other times, so there's no identity here. I just think this is all, you could say gas is coextension with a swarm arranged gas-wise, but that's not helpful. If you can't do coextension of entities, how could you do association between between the properties? How on earth could you say anything like swarm about quantum fields? I don't think there's any way of making progress there, and you were presumably meant to be doing these kind of identifications all the way down. So you're meant to be saying there's something at the really base level that's identical with something all the way up, and then you do this kind of tier of identity. So I just don't think this is the right way to be proceeding philosophically. I think the right way to be proceeding in order to understand interlevel relations is to look to mathematical derivations of the relationships between the theories holistically, collectively, rather than trying to say one bit of the world is identical to one bit of the world at the lower level. Maybe there are property associations, but again, kinetic energy and temperature will only be true for ideal gases. It won't hold for gases with infinite electric potentials and quantum effects. It doesn't hold for solids. Bridge laws can be constructed in principle, but why think that that's helpful? Why think that works? I just don't think that bridge laws shed light. I think this is a poor regulative ideal. I think that it's attractive because it seems to have this kind of air of rigour, but I don't think it's the right way to proceed if one really wants to understand the nature of the relations between models or theories at different levels. Okay.
Sorry, Alex. Do you think bridge laws are uninformative, or not that informative, or not always informative? Like, how strong is your anti-bridge law? Because on the slide you say that it's a special case. In some cases they use.
In some cases they could in principle work, but I think in general they're uninformative, and I think they're a very poor regulative ideal.
But that seems like so they can be useful, but we shouldn't think that that's what we should always aim for, I guess.
Yes, it's unclear to me that they are useful in any but very, very few cases. And I think even in the cases where they seem useful, they might be unhelpful if one wants to understand the rigorously in the veridical sense of rigorous. Mm-hmm. Yes, good. As I said, this talk is extremely non-rigorous. Okay, so I think the example of phonons is a clear example to illustrate what's wrong with this idea. So at the lower level, you've got these kind of particles arranged in crystal lattice, but I don't think there's any kind of identities or associations that you can really construct between individual phonons and individual particles. What you can do is, you think of phonons like a sound wave or a quantization of a sound wave, which roughly talks about the collective excitation of the entire lattice. What you have to do is you have to identify a phonon with the entire thing. And that's going to be right. There's going to be some kind of very broad things you can say about this system is the same as this other system described in a different way. But the standard way in which people presume that you can proceed with something like Lagrangian reduction is to pair up the entities and then to do a derivation. And I think that's the wrong way to proceed, and clearly it's not going to work, or I'm not sure there's any way I can see how it could work in something like a phonon idea. So once the individual phonon, once you've got the particles organised in this structure, you can talk about the harmonic approximation, you can see how the collective vibrations can be quantized and realised phonons. The explanation involves describing the lower level conditions that allow phonal dependencies. I think like a lot of my work, insofar as anyone's read any of it, and I can't like recapitulate stuff here, but is kind of trying to give some kind of non-rigorous explanation of how we should understand intertheoretic relations. And I think that that's more helpful, obviously I would think that's more helpful than trying to construct particular identities and doing particular derivations or deductions, as various different people call it in literature even nowadays. I think that one needs to do something like these kind of explanations of the adequacy and applicability of a high-level description, building on the specific derivations that are developed in the physics literature, rather than trying to shoehorn or gerrymander this into a kind of Hegelian model. So I think this kind of reduction that you can proceed with phonons, I think it's pretty obvious that phonons are reducible in one sense, not in an ontologically eliminative sense. But I don't think there's any good reason to think that phonons are over and above in the sense of they have properties or features that are just in principle underivable from the lower level. And so I think one can proceed with a reduction and one can explain the applicability of the phonon model in lower level terms without requiring that we proceed along this kind of formal Hegelian route. Okay. So to just relate this to some things Wallace has said, there is no way to identify quantized vibration with any atom or collection of atoms in the solid. Best low-level translation of there are such and such phonons present would be the solid is vibrating such and such a way. So this is again to kind of go against the entity association ideas. So the general thought is that the Hegelian way of doing reduction leads us astray. What's important is the expressive capabilities of mass exceeds that of first order logic and natural language. So mass might be reducible to logic in some kind of logicist tradition, I don't know, but you absolutely sacrifice perspicuity in that translation. And I think perspicuity is an important aim of philosophy. Okay. Wait, how long have I been speaking for?
About 17 minutes.
17 minutes? Oh shit. Okay. Okay. So there's a fun idea in Mark Wilson that we can understand collective, why is it that we can't join up, like identify things one-to-one all the way through our material, is because there's something like this thing he calls distributed normativity. So we can't understand how this, how each of this lever works in this mathematical gizmo for translating y to log x. But you can understand how the thing collectively works. And I think similarly one can think of phonons as collectively realised by the lower level material without there being particularly entity identities. Okay, I'll skip over Mark Wilson quotes that take too long, and I'll skip over this. But I think Fourier transform is a really good general reason why it's not the case that we can do entity associations or entity identities. So I think thinking about Fourier transforms as involved in many derivations of one model from another, or the kinds of mathematical relations that we're interested in, is a sign that the Hegelian model went wrong, or good. Okay. Come back to that. Okay, fine. So I'll skip this as well. Okay. Oh yeah, I also think that worlds and Everett are a really nice example of you can't identify an Everettian world with something in the lower level description, but you might be able to derive that. So any attempt to do reduction on the Hegelian model that involves some kind of identity between the quantum and the classical would fail on something like being able to provide a reduction of these Everettian worlds, but plausibly you can give reductions in other terms. And so I think that the requirement that we follow the Hegelian model is misleading. Okay, that was part one. That's a formal model of reduction that's very popular. But there's the other kind of formal model of reduction, or the model of reduction that people go to in the philosophy of physics literature, goes on the name Nichols reduction. So what does Nichols say? Nichols, in fact, says stuff that I agree with. He says in a broader percent reduction in 2, so his reduction 1 is a Hegelian reduction, he distinguishes it from reduction 2. He says reduction 2 is also derivational. Mathematical derivation is a phrase commonly used, includes not only logical deduction but limit process approximations of many kinds. So he's saying, like, let's not think that reduction in general involves logic. Reduction in general involves precisely the kind of mathematical tools that we find physicists using, right? By contrast, reduction 2 does not involve a theoretical explanation. I think that's because he's stuck with the deduction on logical account of explanation, so I don't think that he means explanation in kind of, he says the main function of reduction 2 is justificatory, heuristic. Development of new theoretical ideas is heuristically guided by the requirement these ideas yield certain established results of a special case, often quickly justified to a degree by showing they bear a certain relation to predecessor theory. Justification derives from the fact that reduction shows the successor theory to account adequately for the structured domain of phenomena inherited from its successful predecessor. So if one takes this to be the claim that we should pay attention to the way in which physicists relate theories one to another and the set of tools they use, including limiting processes, to provide a general account for why one theory obtains in a given domain, then I think this is exactly right. If, on the other hand, one understands this in the way that Patricia Palacios understands Nichols reduction, where she makes this into another formal model of reduction, I think that this is again potentially misleading and unhelpful. Because I think this is trying to make it too rigorous, or trying to make it too precise, and I don't think that that is as helpful in understanding the way in which the physics works, or the way in which the world works. So she says, special case of Nichols reduction, limiting reduction, refers to a case in which transformations consist of mathematical limits, and then you've got a way in which you can just understand one quantity as a limit of another quantity. And the condition that the limiting operation makes physical sense, which is to help with a bunch of literature about whether or not bridge laws can involve limits, and I'm not sure any of that literature is particularly helpful in understanding the details of intertheoretic relation. Okay. So let's talk about the quantum classical transition as quickly as possible. So, has been subject to a long debate. Batterman and Berry worry that quantum classical reduction must fail because the H bar tends to naught its limit is singular. So there's an extensive literature on singular limits, but Roeseler, 2015, develops a different response. He claims that reduction in the empirical sense is a three-part relation between two theories that also pays attention to the world. So we divide empirical reduction, where we've got relations between theories that also pay attention to what the world is like, and then he has also formal reduction, which is just a formal relation between theories. And I think Roeseler is right, that what we should really be doing when trying to reduce is to understand how theories are related to one another by paying attention to the extent to which and the context in which they're successful, and looking at those success and looking at those empirical results and being much more, I guess, heuristic rather than rigorous, if that's a helpful distinction. He then looks at decoherence to provide an account of the relation between the quantum and classical, that he claims provides an empirical reduction, subject to the success of this research program. And I think he's again right, that if you really want to understand the details of the quantum classical relation, you want to understand where classical mechanics applies, or where various different classical models apply, and where various different quantum models apply. And you want to use the quantum to explain the applicability of the classical to various different domains, and you need to pay attention to decoherence. Because this will tell you where it's the case that a very, very, very small system that is interacting with some kind of external degree of freedom will end up behaving classically. And very large systems, or relatively large systems that are well controlled in the right kind of conditions, at the right kind of experimental conditions, will end up exhibiting quantum effects. No limiting process can give you that degree of specificity. Decoherence is the right way to understand how it is that quantum gives rise to classical on a detailed, specific way.
Sorry, Alex, did you want us to not interrupt you or to interrupt?
I think that given time I should probably just proceed and then so I might say some things that will resolve whatever you're thinking. So Feinstein says we will take for granted, so Ben Feinstein has this really, really interesting element on the quantum classical relation, which is ridiculously rigorous, really, really using a lot of the techniques and mathematical physics in order to understand the relationship between quantum and classical. And he spurns decoherence methods. He says that this isn't the right way to understand these relations. He says we will take for granted that intertheoretic reduction, if one is possible, will be constituted by an explanation of the success of classical mechanics on the basis of quantum mechanics. I agree. He says empirical reduction on Rosala's model answers the question why, if the temporal evolution of a physical system is better represented by quantum dynamics, can one approximately cover predictions of how expectation values and probability values change in time in classical dynamics? What would be more substantive is if one could establish a stronger claim there is a fixed error bound such that the classical predictions lie within that error bound from the quantum predictions no matter what state one began with. And I think that's really interesting that he says no matter what state one began with, and he italicizes that. And I don't think that's what the goal should be. In fact, I don't think that goal is compatible with this goal of providing an explanation of the success of classical mechanics. Because what state you begin with matters for the way in which decoherence will occur and the way in which locally classical mechanics will come out from quantum mechanics. I don't think it's the kind of thing that could be state independent unless one does it in the limit and one just thinks about the quantum, like all the way up to h bar is 0, all the way down to h bar is h bar, and just compare those two cases. But if one's really interested in the context which physicists tend to black box, the physics avoidance kind of context, then one's interested in contexts in which we can't be as general as this. And so this is why the kind of takeaway is that rigor invites a kind of generality, which I'm not sure is consistent with the details of the mathematical physics complexity of the world. So what does Feinstein do? He does strict quantization, which treats classical correspondence by the h bar tends to naught limit, understood the genuine limiting relation. Conditions are basically the idea that in quantum mechanics you've got commutators, and in classical mechanics you've got a Poisson bracket, and it's a kind of careful way of showing how quantities change from one to another as you send h bar to 0 and you get out commutation, and you get your observables commuting in one theory and your observables not commuting in another. And so then you can show and apply this to a number of very, very general example systems like a particle in external gauge field. Good. So which circumstances is classicality emergent? Why can that question be answered? Why should that question be answered independently of the state you began with? So decoherence theory provides a detailed account of how quantum effects are screened off in certain conditions. Insofar as interference terms are heavily suppressed, we can derive classical behaviour will be exhibited. Mathematical and empirical results tell us which systems in which circumstances this will occur. I think the h bar tends to naught limit is far too generic to provide that detail. So if you think of the limit as expressing the ratio of the action to h bar, there are systems with low energy, so h bar has a kind of units of energy times time. So there are systems with very low energy, small time scales that are subject to decoherence behave classically. There are systems which are large, i.e. high energy, long time scales that behave quantumly if you set the experimental conditions right. And so it shouldn't be the case that we just toggle this parameter and are able to extract where quantum mechanics applies and where classical mechanics applies and use quantum to explain the success of classical mechanics, because it's much more sensitive than can be provided by just this kind of fairly crude toy of toggling h bar. So my general question then is, Feinstein answers correctly h bar tends to naught limit, we need an answer before the limit. So I think Feinstein's approach can't provide a complete explanation of the success of classical mechanics. So here's my general question. What does a rigorous account of quantum classical relations achieve? What does this Fine-Cycle approach achieve? Because I don't think it provides a reduction on his terms by an explanation of the set of quantum mechanics. So he claims that his account explains the structure of the classical quantities and why they obey Hamiltonian dynamics. I do think they can explain all this because there are quantities that there are quantities that are classical in the relevant sense and obey Hamiltonian dynamics. That happened before h bar goes to 0, well before h bar can be thought of as negligible. And so it doesn't provide a full explanation of that, it may provide a partial explanation of that. Landsman's project, he cashes this out in Bohrian terms. He says that we should think about classical as essential to considering the apparatus of the world. I think there's something here, but I'm not sure it's too much to talk about. Maybe this is complementary. Maybe you can conclude ironically and just say, this is one approach to thinking about reduction that partially provides an understanding of how the structures interrelate, and then you need decoherence as well. I think that's probably right, but I think a lot more needs to be done to understand how these interrelate and how they work together. Karim suggests that we can understand similar kind of tools on sort of reduction structural realist lines. I think maybe that's part of the story. Good. Okay. So my last thought, I'm probably way over time, right? No? Okay, cool. So my last thought is that there's a trade-off between rigor and universality. So absolutely specific context can of course, at least in principle, be described with absolute rigor, because the world is consistent and physics to describe the world can be consistent and developed rigorously in order to describe the arbitrarily specific context. Maximally general contexts, I think, might in principle also be describable rigorously. It's the intermediate that I think rigor might struggle with. So describe some phenomenal pattern that's multiply realised, and I mean this in a very general sense of multiply realised. The approximations or idealizations may defy rigorous methods. The thought is that decoherence theory describes what goes on when interference is heavily suppressed. But that's a very, very vaguely described general kind of phenomenon. If you want to describe that rigorously, then you go to specific cases. But what Fine-Cycle says is he wants something very, very general. If he wants something very, very general, what he can do is deal with h bar equals h bar and h bar equals naught. So he can't really deal with the complexity in between that. What you could do is provide a specific model of a specific system and show how decoherence will work in that system. But if you try and do what lots of people are interested in, which is understanding in general how classical mechanics supervenes on quantum mechanics, I think you need a level of generality which involves a kind of vagueness which is not especially amenable to rigor. So decoherence involves the context-specific details of locally describing variables. That's manageable rigorously in a particular case, but if you want to describe decoherence generally, I think it's going to be really hard to get the level of rigor that people are generally after. You want to say something very general, you might give up on rigor, or you say something so abstract that it loses at least some of its applicability. Fine-Cycle and Landsman seek something absolutely general. I think the cost is they describe the extremes, quantum and classical, without being able to survey the subtle in between contexts where the interesting physics takes place, and that's kind of Wilsonian physics for you. Okay, cool. Okay, so, Nichols and Kelly reduction may be available, informative in some contexts. So some of the things I said were a bit too strong, a bit too dismissive. I don't want to be ad hominem. I think there's loads of really important and philosophically interesting work done in lots of these domains. But I don't think they serve as a good regulative ideal for reduction. In fact, I think they mislead. If you just do the formal rigorous stuff and then you stop. And I think that's what lots of philosophers end up doing. I think they'll in conversation they'll be able to do all the rest of it. But in their papers, they'll do all this formal rigorous stuff. And I think that's a mistake, and that's unhelpful, because the world is much, much more complicated than the rigorous application this model will allow. Mathematical derivations, formal approaches serve important functions, but you shouldn't attempt to hammer them into a preferred framework. Okay, thank you.
Questions?
Thank you very much for the talk. I had the impression, so hearing this presentation, that there might be two different senses or meanings between, from your worries about rigor. Would you be okay with distinguishing maybe? So the last point you made was there's a trade-off between generality and precision. Maybe that's one of them. And the other one that doesn't seem to be identical to me is that sometimes relying on formality and formal apparatus can lead you to wrong questions. That's the understanding that I got from the Hegelian reduction or first order logic kind of language points that you made. And it's not obvious to me that the two are sort of the same thing. How do you think about this?
Good. Yeah. I think that's really helpful. I don't think those two are the same thing. I think there is this trade-off between generality and specificity and the complex relation with rigor, and then there's other way in which I guess that's a sense in which rigor can lead you to ask, the goal of rigor can lead you to ask the wrong questions. You might want to ask, what's the behaviour of this theory like in that limit? And that's a question to ask, but it might not be the salient question on which you should be concentrating. But it might be the only question that your rigorous mathematical tools allow you to ask. And so if you've got a set of tools available to you and they only allow you to ask certain questions, then you might end up asking those questions because you want to use those tools, rather than asking a different set of questions that might be more interesting or more important in some sense. So but it's not always the case, I think, that these trade-offs between specificity and generality will be the same as the leading you to ask your own questions. Yeah, thanks.
Judy?
Yeah, thanks. This is super interesting. Just on the point about the trade-off between generality and precision, I'm wondering, I'm going to play advocacy of rigor here, but I think we probably will agree. I'm wondering if the problem is not rigor per se, but the problem is a sort of overconfidence in the applicability of your theory or hypothesis. So the situation that you're describing about Hegelian reduction is that they're just overly confident about the scope of the applicability of Hegelian reduction. There are some situations where one theory reduces to another, but we cannot have the identification. And I think a person who you might think is non-rigorous might also make this kind of mistake, right? They can claim that by intuition that this sort of equation should hold in this domain of applicability and think that the math will just work out. And I think that's a similar kind of danger that you're identifying. And in that case, they're just overly confident that the math will work out. And when some people try to, I'm also thinking about Kareem's situation, right? When some people comes along and try to rigorify that particular equation and discover that it only holds in particular conditions, I think that's sort of responding to that kind of overconfidence. What I'm wondering what you think.
Great. So one thing I forgot to say, which I meant to say, was that, the true veridical pursuit of rigor is always good. in the sense, like, you know, I'm just like, understood tendentiously, like, you know, if it's the right kind of rigor, then it's great, because that involves paying close attention to the details of the physics and understanding exactly how it works in each specific domain. But I do think that there's a kind of, and this is a socio-psychological hypothesis, that...
I'll talk about that.
Yeah. But there's something alluring about the idea of, you know, look at these models of Hegelian reduction. You've got a logical deduction. Surely, if you've got a logical deduction, then everything's kosher in your philosophy. Or, you know, you see this all the time in undergrad essays. They'll try and construct something as like a logical inference. They'll sometimes get it wrong, but you know, when they manage, they're like, okay, well now I've done something really properly philosophical, without trying to think about, like, you know, it's not just validity and soundness that are important. It's kind of whether or not this is the right argument for this context. And so I think that, like, I agree with basically everything you said, but I do think there's something about the allure of rigor which is misleading people here into thinking that the Hegelian toolbox is like has broader applicability than it in fact does. Right, but the you know, in some sense, a properly rigorous thing to do is to not apply it where it's inapplicable. And I think that people haven't noticed that it's less applicable than they thought it was, maybe much less applicable than it might seem.
Thank you. Thanks, Alex. This might sound like a non-rigorous question, but I was wondering, in a sense, like, is rigor scale relative? So, like, if you understand scale relativity as not just an ontological physics, but as a kind of like methodological, epistemological physics, the idea, in a sense, is that you're kind of like trying to have the right mathematical tools or models to represent adequately the different bits, the different scales that you're dealing with, right? So then maybe it's not that you're less rigorous with the move between the scales, or that the rigor should be, that you should be less rigorous, but in fact that the rigor is kind of like the same, but in a scale relative way. Does that make sense?
I'm not sure.
So I'm pushing back against the idea that you should be less rigorous just because you have, like, you're moving between scales and so on. It's just the norms would be different for different scales in a sense, because you're kind of like assuming that you need the same kind of like physical-mathematical apparatus or norm of rigor to deal with the different ontological scales. But you should just adopt a kind of like a complementary methodological epistemological principle by which your norms of rigor would also be adapted to the relevant ontological.
Am I misconstruing if I connect this up with some of the things Kareem was saying about, like, the particular physics community will have its own standards of rigor, and so, or are you thinking of them more like a kind of, you know, we could draw like a graph and look at the kind of, as scales change, the standards of rigor should change in some kind of like monotonic way, or?
I suppose the latter in a sense.
So
I'm kind of like happy with kind of what Karim said in a sense, but I think I wanted to know whether the stronger version.
I don't want that to be true, no.
Okay.
Because I think that we can, I don't see any reason why we can't describe the world extremely rigorously at lots of different scales. Maybe at the, you know, human scale there'll be some kind of mathematical tools that will just be inappropriate because...
But that's what I'm saying.
Yeah. But I don't know. Yeah, maybe. What's the biology should be
less rigorous at the interrelationship levels, and I'm saying, well, no, you can be equally rigorous. It's just not going to be the same kind of.
I reckon if I was thoughtful enough, I could come up with good counterexamples to monotonic claim, which wasn't your claim, which I imputed to you.
Yes.
Yeah, I reckon there'll be a kind of scale relativity of the applicability of rigor, sure, but it won't be. Yeah, it won't be a simple function. It'll be a complex function.
Okay.
Not complex in an imaginary sense, but yeah.
Great.
Thanks, Alex. I really liked it. I think I want to push back on maybe the necessity of connecting up the different bits in the way that, I mean, not you do, it's the literature does, I guess, right? In particular, I think there's no problem at all in having the H-bar kind of procedure being tied to specific models. And in principle, you could have a very abstract notion of decoherence that was tied to a limit. So I feel like I agree with you in the sense that like strict use of completely general, state-independent, limiting methods is the wrong way to think about emergence of classicality. But I think Valentine and all these guys, ultimately what they were talking about is the detailed, messy physics of using H-bar expansions in dynamical systems, looking at the spread of the wave functions, the higher order moments, blah, 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 right? And in those cases, there are some systems where you can use, like, let's say, ignoring terms order H-bar cubed is going to give you a physical insight, and you can start exploring the semi-classical domain.
Yeah.
And it's not the case that you're always going to be able to do the same job or a better job with decoherence. So I feel like I want to decouple using, I think there are two tools for it. They are the most powerful two tools for exploring semi-classicality. Probably in some, decoherence is the more general one, but they're both useful in different contexts. And I think I wouldn't want to lump all of the use of H-bar into this generalist, rigorous strategy. I think there's lots of stuff to do in messy little models with that as well.
Okay, good. So a longer version of this talk had the thought that I haven't developed as much as I would have liked, that there's a decoherence-based explanation for the use of H-bar as a proxy, which is that one can understand, I mean, like it's clearly, like, you know, if you just think of H-bar as having quantities of energy times time, you're going to think about the strength of interactions with external systems, and that will be parameter in terms of energy, but then there will also be a frequency in terms of time.
But then you want to reduce the two motions of reduction to one.
I think that you can use a detailed understanding of decoherent, of like regime specific decoherence to understand why it is and when it is that the H-bar limit is a useful way of understanding classical quantum. So it's not the case that
we have time.
We have a bit of time.
The H-bar limit can often work, but where it can and where it can't, we can explain that using decoherence.
But I mean, in practice, we do use H-bar to do physics, right?
Yeah.
I mean, why do you want to reduce it all to decoherence? Why is decoherence being the explanation so important, right? And we've got these different tools. Why don't we keep using both of them? I feel like there's a tension between your anti-rigor and kind of pro-specificness strand and your, like, decoherence is the ultimate explanation.
The decoherence, I think, provides a physical mechanism, whereas I don't think H-bar provides a physical mechanism.
But it does, I mean, exactly in the sense I talked about, right? That you can think about expansions where you have sizes of effects measured by H-bar and statistics of like how the spread of the wave function moves over time, like how the when the Ehrenfest equations apply, when they don't, and you can do this all for states which already have the coherence suppressed, right? So I agree with you. I just think that we don't want to throw away everything from the H-bar stuff and just put it all.
No, so absolutely. I think they're complementary. I guess my thought was that one, to use an ugly term, grounds the other. But that might be overstating the case, and I need to read some of the Valentine stuff that you're talking about, so I'd like to...
I mean, Valentine and Val, they're the other extreme, right?
Yeah.
They think you never need decoherence, you can do about it in time.
Yeah, so
I think that's...
So I should read that stuff, though. And so yeah, like references for that.
All right. Shall we thank Alex one more time, please?